Oh, hello. Who's
Sorry
that?
about that. Kids.
Kids. That's what that. No problem.
I'm going on mute.
No problem. All right, let me get myself in here. Looks like I've got to put my email in every time. It's kind of annoying.
Sherry Leprod and Cheryl Leprod, you and your twice.
Yeah, we have some twins in our class.
Oh, right. Yes, I remember now. Yes.
Yeah. I see their pictures. You guys got to show me your face one of these days. You're going to have to for the test, you know. All right, now I'm going to let myself in here. Admit all. In fact, let me get rid of the waiting room. Hopefully I got into here. Okay, good. Connecting. No, we don't want audio. Continue.
So do you prefer to be called doctor? Since you technically are one? Okay.
Yeah.
I have a question for you then, doctor.
Okay.
Is it normal? It's like I'm on the homeworks and I feel like I can get 90% of it, but it's like something, is it normal to just not feel it clicking? Like I can get the problems right, but it just doesn't feel like it's there, if that makes any sense.
Yeah, I remember definitely having experiences like that in upper level math classes. Yeah, just keep working on it. Sometimes you finally get it to click when, right before the test or, when you're really studying. But
usually
as you're
it's the
doing
class, the class after is when you finally like, oh.
Yeah, there's that. Absolutely.
All right.
Yeah. Oh, man.
And I was
Yeah,
wondering,
I was like, go ahead.
me and wife wondering, how do you do a thesis in math? Like, what
So
does
you
that even
prove
look
stuff.
like?
You prove
Like,
theorems. My master's degree was more computing. And so I actually did, I tested an algorithm to see how much kind of round off error it would propagate. So that was my master's degree, but my PhD, my dissertation was proving new theorems and coming up with new math. So it's pretty intense.
wait. So you actually made new math?
Yeah. But
wow.
it's so far out there though. It's like, it would never be used for anything.
I doubt
And
that.
sometimes I think in fact I have called it kind of some sort of mind games. What was the word I used for it? I don't know. It's just, logical mind games. It's upper pure mathematics. You're using a lot of logic, but you've got these structures that have certain characteristics, and so you prove things about those structures based on those characteristics. And yeah, and so much has been done already that you have to come up with some really weird structures to get any results. And the hope is that eventually there will be an application for this stuff. And then my PhD professor was really well known for all of his pure math that he was very prolific and just writing papers and coming up with new stuff, and got lots of money, lots of grants from the National Science Foundation, I think NSF, because of the idea that pure math, does sometimes eventually get, find its application somewhere. Quantum physics. It was like, oh, here's the math that we need for this.
So you weren't doing applied mathematics. You were doing pure mathematics.
I was doing pure math. Yep. Yeah, for my master's degree, that computing was more applied. But for my PhD, it was all pure math.
Oh, that's like Clifford algebra and smooth manifolds. And
Yeah. We had some. Yeah, we take, abstract algebra was more my field. But there's also something called topology, which is kind of like what you're talking about with manifolds, and kind of an abstract geometry.
don't tell me you worked with Riemann hypotheses, did you?
Riemann hypothesis.
Or like P equals NP, or
That doesn't sound familiar.
four-color theorem, Fermat's last theorem.
I heard about that Fermat's last theorem. I heard about that, and was real excited when it got proved. But no, I was more on the logic side with the continuum hypothesis, and proving what if results were undecided, meaning they could be proved true in one set of axes and false in another set of axes, and so that they were actually independent of
That's the genius
framework.
level math right there. There's this thing I'm looking at that shows like basic and serious. You're in that genius level math.
I was
That's
really
scary.
serious. I was, yeah. My father got his PhD from Harvard, so I have some genetics. Yeah, and then just I don't know. I love teaching so much that I decided not to pursue it. So, but that's but it was wild for a time there. All right, we got to get going on this stuff. So did everybody say something in the chat? Hello here, Bueller. Awesome. Good. All right. So we got fun stuff to do today. Some people will think it's fun. It's applications. It's actually my least favorite. Now, not coincidentally, but that now that you've brought up that I'm a pure mathematician, I like the stuff that's just logic. This step to this step to this step, the stuff where you've got to apply it, you've got something like Newton's law of cooling and what else? The rate of decay, those problems aren't too bad. Circuits. Yeah, those I'm not as fond of, but for the most part, the formulas are there, and it's really just a matter of applying the formula. So, and then here also we're solving differential equations. So the formulas involve differential equations. So you plug stuff in to the formula, and then you solve your differential equation. And most of these are going to be giving you initial values. So then you will actually find, your arbitrary constants and get the specific result. And then some of the problems, once you find the equation, the function, then they'll ask you to use that function to find some value for a given value of time or whatever. So fun. And I just today, as I was looking in WebAssign for prepping for the class today, I just saw that there's like 10 messages. So is there anyone that wants me to answer those? Is there something that I should answer maybe with the class so that everybody gets
do we have time to review a homework problem?
Yeah, like if you asked, if you submitted something about a homework problem.
I didn't submit anything through WebAssign.
Okay, cool. Yeah, if you submit something through WebAssign, I just forget that it's there, and I couldn't figure out how to get it to forward to me. So if you want me to answer it, just send me a separate email saying, hey, I sent you a message through WebAssign, could you check it out? And I'd be glad to. I just forgot to, but I'll look at it tonight after class and see what I can come up with. There were a couple problems from section 1.2 homework that I might delete. Had to do with, where is this defined? Find out open rectangle, to where this function is defined, or where the solution exists. And, it had to do with the existence theorem for a solution, and that's not important. So I'll probably just see if I can delete that question, or else give everybody credit for it. All right. So yeah, what's your homework question?
It was section 2.4, number 14, and I can read what I wrote down. Hopefully I have
Yeah,
it.
let me get my tablet going here with a fresh sheet of paper, and I will write it down. Oops. I keep thinking I'm going to get faster with this stuff, and I'm just not. It's like, I can't wait to go back to the classroom. Okay, go.
It's negative xy sine of x plus 2y cosine x dx plus 2x cosine x dy equals 0.
Let me read it back to you. Negative xy sine of x plus 2y cosine of x dx plus 2x cosine of, cosine of what?
X,
Cosine of x dy?
yes.
Somehow I didn't put the x in there. Okay, got it. All right, now let me try to show you guys my tablet. Let me see if I think I need to give myself permission here to share. And then I should be able to. Boy, we got a full class today. Good deal. Okay. There it is. And then what's my magic combination to make that menu go away? Shift, Control, Alt, H. Yep.
What problem was this?
Yeah, say that again. What problem was it?
Number 14 on 2.4.
Thanks. All right. I'm going to switch to a different color too. All right. So 2.4, I believe, was exact. Now, is there any parentheses in there?
I have parentheses. I'm not sure if they were in there or not, but I had one in front of the negative xy and then after or right before the dx there.
Okay, that's important.
Yep, and then I had one one in front of the 2x cosine x and one before the dy.
Perfect. Okay, so that's really good because then that's our m and that's our n. So we want to check, is my equal to nx, right? To see if it's exact. And it has to be in that form, you know, m, some function of x and y times dx plus some function of x and y times dy equals 0. So yeah, those parentheses are important. All right, so let's see. Oh, I hate when that happens. Jumps around on me sometimes, and don't ask me why. All right, so the partial derivative of m with respect to y is what m sub y is talking about. And that's where we let x just be, x just be a number, and y is your variable. So that means that's a number and that's a number. So it's really just like a coefficient of y, and so its derivative is just the number. All right, it's kind of like 5y, the derivative would be 5. All right, and then for this other part, cosine of x would just be a number because x is a number. 2 is obviously a number, so similarly, the derivative of that with respect to y would be 2 cosine of x. Okay, so now we want to look at the partial of n with respect to x. And that's going to involve the product rule. We've got a 2x and a cosine of x. So I'm going to copy the 2x. I'm going to take the derivative of cosine of x. And then I'm going to take the derivative of 2x and copy the cosine of x. And voila, they are the same. No, they're not. They're not the same.
That's where
We're trying to prove that
They're not the same. So this one is one where it's almost exact.
So this is where you would do like the nx minus my over m.
So what is the difference of these? The difference would be, oops. If I subtracted this whole thing, then it would be a positive x sine of x plus 0, right? Would be my minus nx. So then if you look at the handout on, exact at that, that formula, there's right here. Right, it's here. So if we divide it, the difference in the other direction by m, and it's a function of y, then we can use that. Okay, so that's what we want to refer to. Let's see. Dividing by m or n. Let's see if we get a function of y if we divide by m. So if we take this and divide by m.
I have a quick question.
Hmm.
We did the nx minus my, not the my minus nx. Is that wrong?
We did my minus nx. It's just going to be off by a negative.
Okay.
So, yeah, so if we need the other, then we'll just add a negative. Like I'm going to do this one.
How do you know which one to use?
Well, so you just take the difference and you look and see if here's the difference. And you just take difference either way, right? Like I did. And then you go, well, if I divided this by m, would I get a function just in y? No, I'd get a mess, right? But if I divide this by n, I'm going to get a function just in x, aren't I? That's going to be 1/2 tangent of x. So is that what we want, or is it the reverse? M minus n over n. That's what we want.
The problem said use the integrating factor mu equals xy. That was in the problem.
xy. Well,
was it parenthesis x comma y?
If they're telling us what to use for an integrating factor, then that saves us this work that I'm doing right now. Because that's what this basically is developing, is finding a good integrating factor to make it exact. What's that? What was your question?
No, I'm not sure. I don't have the question in front of me.
So, gotcha. So this finding out that difference in either order divided by either m or n gives you a function of either y or x, then there's an integrating factor. And I think the integrating factor we're going to get is not just xy, because we've got a tangent.
It says that it says multiply the given differential equation by the integrating factor mu of x comma y equals xy, and verify that the new equation is exact. That's the specific question.
Okay, so we don't need to do all this, but this might work if you actually did this. It's another way. We'll call this mu of x, that would also make it exact. So, but they, yeah, since they said use the integrating factor mu of xy equals xy, that means that we can actually do it that way. If we multiply through by xy, let's see, that's going to be negative x squared y squared sine of x plus 2xy squared cosine of x dx. And the, oops, keep it small, I guess. The other one would be 2x squared y cosine of x dy equals 0. How's that look? Multiplying through by xy. Got an extra xy here, got an extra xy here, extra xy here. Yeah. So let's check it now. My is, now we just want to bring that 2 out in front and decrease the power because it's just, y squared times a number. So 2y times that number is the derivative there. And then the other one, same kind of thing, bringing the 2 out in front makes it 4xy cosine x. And then nx is, again, we're going to have to do product rule. Let's take the 2x squared y. We don't have to use product rule there because x is, wait, this is x. Okay, so y is just a number. So that is right. That is just a function of x right there, that first factor. And that's a function of x right there. Okay, so I'm going to copy 2x squared y times the derivative of cosine of x plus the derivative of 2x squared y, where y is just a number, is going to be 4xy. And then copy down the cosine of x. How's that look? That's exact, isn't it? So then you should be able to actually solve it by taking the integral of m partial integral with respect to x. Let's see. Yeah, that's going to involve doing parts. Does it say to actually solve it or just check that it's exact?
It says to solve.
Okay.
4 times.
What?
You end up doing it like 4 times.
Yeah. Y'all want to see this? We should probably do this, or I should do
Tabular
this
method.
later. Yeah, the tabular method
method
would be good.
helps.
That's right. I always forget how that works. It's a neat thing though.
Positive, negative, and then you do your first all the way down to 0, and then whatever keeps flipping, you put it in the last column.
Okay, so positive, negative. So if we do this for this first one,
And then we would put liate, L-I-A. So that would be our sin x would be our dv. So that one we don't use yet. We would use that negative x squared y squared. And you would just keep listing that until it went down to 0 to the right of positive, negative.
So derivatives of u with the first derivative being positive?
Yes, and just keep doing the derivatives of u until 0.
So negative 2xy, because it's just with respect to x, and then negative 2y, and then 0, okay?
In your third column, you'll have sine, and then it'll go the derivative of sine, which takes it back to negative. Nope.
Now I didn't put u. I didn't put u on here. I started with the first derivative. Do you start with u or the first derivative?
Start with the first derivative.
Okay. So this is du.
And then
then here we start with sine of x, or it's
sine of x. Sine of x, and then cosine, and then negative sine.
Wait,
then
are we doing
Wait, that
integrals
doesn't-
or
Those don't match
we go
up.
integrate? We go integrate, don't we?
backwards. Yeah, I think I'm doing it backwards.
Yeah, the last column is going to be its integrals, and you start with the original function on the top line.
Thank you.
Okay,
It's been a
for you
while.
also?
Yeah,
Yes.
Okay.
because what you end up doing is you start with the plus, and you go to the first or the original function, and then you go down and over in the columns.
Yeah, so start with the original function, so that's u, and then its derivative, negative 2xy squared, and then its derivative, negative 2y squared, and then 0. Sorry. Oh, no. All right, and then this one, original function dv, it's integral, right? It's antiderivative, and then it's antiderivative. Okay, and then we've got uv. There's uv, right?
Yep.
So that's going to be a positive x squared y squared cosine of x. And then what?
And you do the same circle down, so it would include that. Yep.
But that's going to be positive, isn't it? Positive. So plus 2x
I think
y
the first one
squared.
is negative, isn't it?
Well, because it had a minus in the first column.
Yes, yes. I'm
Got
talking
it.
about the one above. Your,
That one minus, well, plus minus minus.
yeah.
Yeah, so that one's positive. They're both positive, yeah.
Correct me if I'm wrong. It's been a while for me. I believe it is going to be the plus is distributed to that negative, so I think it's going to be negative, and then the plus distributed to the other one makes it a negative.
But we're
And
multiplying.
I'm rusty. Oh, crud. Let me figure this one out.
Oh, man.
For the third line,
Uh-huh.
where we went from negative cosine of x to positive sine of x,
Yeah,
isn't
that
that?
should have been negative, shouldn't have been.
Yeah.
Yeah. So let's do that. That antiderivative of negative cosine is still negative sine. You're right. So then this one is negative.
And then you have a fourth one right below negative sign to match up with that negative 2y squared.
Okay. So that's going to be a positive cosine.
Those are all your
Wow.
terms.
Yeah. Okay. So then we've got a negative 2y squared cosine of x. And that's just this part. So I'm going to, for the sake of time in class here, I'm going to not spend any more class time working on this, but I will work on it outside of class and, show it to you next time if you want.
Thank you.
Sound good. You're very welcome. And, all of you guys work on it too. The tabular, I had that written down somewhere, but yeah, it's, that's exactly how it works. You've got the signs that start with plus, u and its derivatives, dv and its integrals, and then you do those diagonals. So that was exactly correct, what we did there. So this is the antiderivative of that first part of that integral. So then we'd have this part of the integral, and then of course we still have to do the integral with respect to y. So that's part of it anyway. So later, to be continued. How about that? All right. So let's go on to, unless there's another homework problem that we should look at, let's go on to our applications. So I'm going to save that as, that's number 14 on 2.4. So I will actually finish this later. If we do have time at the end of class, ha 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 ha, we'll come back to it. But I'm thinking not. All right, so I just want to open up a new page here. And we're looking at 3.1 applications. But I also want to refer to the handout that is in D2L. And for some reason, I ended up closing that window. So that we can look at what are these formulas that we need for these various types of problems. And then we can look up these various types of problems and work them out. Actually, there's a page of problems that we can use. So let's see. Under, oh, wrong one. Under our course and content. God, it's so slow. There we go. Chapter 3 applications right there. Okay, so let me actually download that so that I can pull it up here. Oops, sorry. There we go. Downloads. Chapter 3 applications. Finally. All right, so the first ones are, I think, the easiest, basically because you should have seen those in Cal 2. You might have even seen them in algebra, college algebra, that whenever you've got a exponential growth or decay situation, the idea is that the rate at which the quantity decreases or increases is proportional to the amount present. Okay, so proportional just means that, one is a constant times the other. And if you have a decay, then that's a negative constant. If you have a growth, that's a positive constant. What happens when you solve this differential equation is that you get an exponential. Basically, this is separable. If I divide both sides by x and multiply both sides by dt, excuse me, and then integrate, I get ln of x equals negative kt plus some constant. And so x is e to the negative kt times e to some constant, which is another constant. So x is, in this case, the amount. Sometimes that's y for various problems. For your textbook, what did they do? I had that open for just a minute ago. For your book, they use P for population. They use X for a general growth and decay situation. Or A for amount of plutonium. So, it can be anything. But you end up with this kind of general exponential situation, either where the constant is positive or negative. So we could have A of t equals the initial amount, which is what that constant always is, because if you plug in 0 for t, that's what you get.
Didn't we? I think we did this in Cal too. I think it was the first
Yep.
section. And
Yeah,
then they just said,
good memory. Absolutely. Yeah. So we've got this future amount times e to kt. All right. So those problems should be piece of cake. So let's move on to Newton's law of cooling. We'll do one. But Newton's law of cooling is when you have something like a hot cake coming out of the oven, and it cools, and its rate of cooling is actually proportional to the difference in the temperature between the temperature of the object and the ambient temperature, like the temperature of the room. Or if you throw something hot in a bowl of water, the ambient temperature, the surrounding temperature is the temperature of the water, and you've got this same cooling property. The problem that you've got in your WebAssign homework that I might go over is a forensic problem of finding a dead body and using the temperature of the dead body to find out what was the time of death. So that's kind of interesting. So that's just basically using this guy. And again, if you integrate that, you get well, you've got a separable situation, and it's easier. Actually, it could be separable or linear. I'll show you one of those. Basically, we'll plug everything in to here, and then we'll solve it. And I'll show you how you can either solve it as a separable, which is usually easier, I think, or you could solve it as linear, which is not too bad because it's a simple linear equation. All right, then there's mixture problems, and here it gets a little bit more complicated. You have to look at the rate of change of how much of a certain substance, like salt, in a mixture, like salt water, brine. You end up having, what's the rate of change of the amount of salt in that mixture if you've got, a certain mixture of the salt pouring in, and then another, and then the stuff that's in there pouring out at the same rate. So yeah, we'll do one of those for sure. And then for you future engineers, electrical engineers, there's circuit problems. Here we're just going to look at the real simplest type. There's more of these in chapter 5 we'll come back to. Yeah, there's really this in terms of charge. You've got R is your resistance. L is used for inductance for some reason. Voltage drop across a capacitor. Anyway, you put these all together in a closed circuit, and you get this equation. You can see that this is linear, because for here, when it's given in terms of Q, the charge, Q is a function of time. You've got the function, its derivative, its second derivative, and then otherwise these are just constants. E could be a function though. E could be another function of t. And then t is your variable like x used to be. It just blew up again for some reason. And then momentum problems. I wasn't going to go over that today. Free falling objects. Yeah, I wasn't going to go over that today. So here are some examples. And I was kind of torn between whether I wanted to go over these examples or go over WebAssign problems. What do you
Is
think?
Unit 3.1 on the test?
So 3.1, what I'm going to do is give you, and I was going to try to have them today and I don't, but I'm going to give you a couple of problems, 2 or 3 problems to do and turn in the day of the test, but it won't be on the in-class part of the test.
Okay.
Yeah, so I'll have those to you by next time. So, and because I still haven't decided if I'm going to give everybody the same problem or if yeah, I think I will, so that you can work together if you want to. So.
Bless you.
Aw.
You can work together on the test.
Not on the test. No, on the test, we're going to come to Zoom and you need to be fully dressed and stuff so that you can turn on your video. And I'll ask to see your desk area, the whole 9 yards. You know, basically all you get is that one piece of paper, and you'll work on your test while we're all sitting here in Zoom, so I can make sure you're not talking to each other.
Hey, yeah, I got a question. This,
Yeah.
When is the test again? Is it on February the 2nd?
It's a week from today. Yep.
Okay. Okay.
So this is the last section. We've actually already covered the material that's going to be on that test. So this section, I'm going to give you a problem next time. Next time is just review. All right, so let's just do these. Yeah. And then if we have time, we can do, we should do that dead person problem. I thought that was pretty interesting. And it works out differently than I thought. All right, so, and yeah, we're not going to do the falling bodies, but the rest of them are pretty. And the circuit problem here, actually, this circuit problem is a little bit harder than what you'll see because it has a function for E as opposed to it being constant. So we'll do a homework problem instead of this problem. If I remember correctly, this makes it get pretty tedious. Got two mixture problems here. That's probably a good idea. Newton's law of cooling, hot pie, and yeah, okay. So growth and decay, it says the rate at which radioactive nuclei decay is the rate at which radioactive nuclei decay is proportional to the number that are present in a given sample. Half of the original number of radioactive nuclei have undergone disintegration in a period of 1,500 years. What percentage of the original nuclei will remain after 4,500 years? And when will only 1/10 remain? Well, this is kind of silly. We don't even need to come up with, for the first question, we don't need our formula. Look at this, 1,500 years. Is this half of them have undergone disintegration, basically have decayed in a period of 1,500 years. So that is its half-life, right? The half-life of a substance is how long it takes for it to decay to half of what it was. So, and that's what happens with exponential decay, is that then in another 1,500 years, it decays to half of what it was again. And then in another 1,500 years, it decays to half of what it was again. So, how much will remain after 4,500 years? Well, if we have, say, x sub 0 is sometimes used for initial amount. If we say x is the amount, where can I write it? X is the amount at time t. So x is a function of t. Then x sub 0 is going to be our initial amount. And we have this situation, you know, where dx dt is a negative constant times the amount present at any time t. And we could integrate that. And we will, because for this next question, when will 1/10 remain? We're going to need to have that equation. But for 4,500, what all you need to notice is that that is 3 half-lives, isn't it? 3 more half-lives. So half have undergone disintegration. So what I'm trying to figure out is if the 1500 years is yeah, okay. So at time t equals 0, we have x sub 0. At 1500 years, we have half of x sub 0. At 3000 years, we have half of that, so a fourth. And at 4500 years, half of that is 1/8. And 1/8 is what as a percentage? 1 divided by 8. 0.125. So what percentage remain after 4500 years? That would be 12.5%. All right, but we do need to actually work out the problem for to find out when a tenth will remain. So let me go back to some paper here. So we've got problem 1 here, and I've got it here in paper too, so I don't have to keep referring back. Okay, so again, we've got dx dt is a negative constant times x. And we have that half, or let me just say the half-life is 1500 years. Okay, so this gives rise to our model being what? Being ln of x is negative kt plus some constant. So x is e to the negative kt, e to the c. E to the c, we actually realize that that's x sub 0. All right, so there's the process that you saw back in Cal 2 as well. All right, so now we can find k by saying, all right, half of x0 is the amount in 1500 years. So I can plug in 1500 for t, and then I can solve for k by first dividing both sides by x sub 0. And then taking ln of both sides. So ln of 1/2 is just the exponent. And then k is ln of 1/2 divided by 1500. And actually, to tell you the truth, I don't really like to have the negative there. I like to just say it's gonna come out negative when you have decay, and it's gonna come out positive when you have growth. Just calculating this number is going to give you a negative constant. Some calculator tricks that are useful. Have you used the store button before on your calculator? You know, when you calculate this, you you get an approximation. Let's see, what does it come out to? ln of 0.5 divided by 1500 is negative 0.000462 blah, 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 blah. So what we can do is store that in your calculator with the store button that's right above the on key as k. And k should be above one of your other keys. I've got my TI-89 here, so I've got a k that's above my EE key. but it's in purple. So I have to hit the alpha button first. So, whoops, let me move that over. So find what letter you want to store it as and hit the alpha key and then the key that has that letter. And then anytime you want to do a calculation with it, it's all you have to do is pull up that letter. All right, so the equation then for this one is x equals x sub 0 e to the kt, where k is this number right here. So now we can say how much, or no, when, not how much, it's a when question. When is 1/10 left? Okay, so you want to know the time for when x is equal to 1/10 of the original amount. So you plug in 1/10 x sub 0 for x, and I'm just going to leave k as k for now. So again, we want to solve, but this time we're going to solve for t because we know k. And notice that the first step is divide both sides by x sub 0. I mean, this should have been stuff you learned when you were studying exponentials. Take the ln of both sides, natural log of both sides, I should say, and that undoes the exponential and you end up with just the power. So then t is ln of 1/10 divided by k. So now I can approximate that by going to my calculator and clear. Approximating ln of 0.1 divided by alpha k. And I got a negative number.
Do you have a moment? I have a question.
Yeah. What happened?
Did you make k negative? Or actually, yeah, it should be a negative value, right?
K is negative.
Yeah, it should be.
Yeah.
Oh. Yeah, on my calculator, I have it stored as a negative number. That's really weird. ln of 0.1 divided by k. I stored. Oh, you know what? I didn't get it stored as k. Yeah, something happened. Okay, hang on. Let me store that as k again.
So, Dr. Champagne, these kind of questions are going to be on the test, correct?
This will be for you to do at home and turn in on the day of the test.
Okay.
Yeah. Negative 4.6. Okay, that's I want to store as k. Why didn't that work? Store as k. I wish I could show you what I'm doing. All right, so then if I go up and do this again, there. Ah, that's more like it. 4,982. You guys doing it too? Is that what you got? And this is years, I believe.
Yeah, that's what I got.
Awesome. Yep, years. Yeah, I was getting like negative 103. I was like, no, something's wrong. It's because I've got my 89 here and I have not worked with this TI-89 for a while, and it's not quite as easy as the TI-84. For some things, it's great though. All right, so that's Growth and decay. Let's do Newton's law of cooling. Number 2. Another piece of paper. Let's go ahead and insert a couple pieces here. All right. So number 2 says Newton's law of cooling. Here, try to show it to you. Where'd it go? Here it is. A hot pie is taken directly from an oven and placed outdoors on a porch table to cool on a day when the surrounding outdoor temperature is a constant 80 degrees Fahrenheit. The temperature of the pie was 350 degrees Fahrenheit at the instant t equals 0 when it was placed on the table, and it was 300 degrees Fahrenheit 5 minutes later. What's the temperature of the pie after 10 minutes, and when is its temperature 100 degrees Fahrenheit? All right, so to answer those questions, basically we need the function for it. And that I noticed is what WebAssign is going to focus on. You know, what is the function? What is A of t is what they like to call it. And then they'll ask you the questions. So we've got the hot pie coming out. The outdoor temperature is going to be the ambient temperature, which is 80 degrees Fahrenheit. Sometimes it's called T sub A, T sub S for surrounding, T sub M for medium. I'm just going to call it capital T. All right, and that's really what it did, what they used in this packet for that function. If you saw, where'd it go? Here. Yeah, the temperature of the surroundings are going to use capital T for this. This is just a simple way to do it. Little t is time, but capital T is this constant ambient temperature. And then X is our variable, our dependent variable. And there's another constant because of the proportionality. Okay, so we've got the temperature of the pie when it was taken out is 350 degrees Fahrenheit at time t equals 0. So we could say that that's X sub 0. Or we could say that it's X of 0. Same thing. Then it was 300 degrees 5 minutes later. Okay, so that tells us that X of 5 is 300. Okay, so we've got this differential equation. And we can plug in capital T. So then this we can solve by noticing that it's separable. Oh, hang on. Okay. And we can divide by X minus 80 and multiply by dt and integrate. So this is ln of X minus 80 because the derivative of that is 1. So a substitution of u equal to that denominator would just give you du equal to dx. So simple substitutes easily equal to kt plus some constant. So it's very similar to the growth and decay. Exponentiate both sides, you get your X minus 80 equals e to the kt with e times e to the c, and that e to the c is going to come out in front, not as x sub 0, excuse me. That's going to come out as c. A different c, but nevertheless, another constant. Oh, different color. All right, so this then is what we can use to find k. Using the initial condition that x of 0 equals 350 and that x of 5 equals 300, we can find both c and k. I like to just do them one at a time. If you plug in 0 for t and 350 for x, you get c, right? Because e to the 0 is 1. So c is 270. So then we have x minus 80 equals 270 e to the kt. Now we can find k by plugging in 300 for x and 5 for t. So that's 220. Divide both sides by 270. And then take the natural log of both sides. Natural log of this, which gives you the exponent. So then k is ln of 22 over 27 all over 5. And again, we can approximate that. Ln of 22 sevenths, 22 27ths, divide by 5 is approximately negative 0.040959. And it's negative because it's cooling. And then if I store that as k, then I can use that when answering the questions. Oh, where did it go? Okay, so questions. What is the temperature of the pie after 10 minutes? Right, temperature is x. So let's get our equation here. Our equation is x minus 80 equals 270 e to the kt, where k is, negative 0.040959. So now we want to plug in 10. And actually, the function itself probably should write with the 80 on the other side, right? E to the negative 0.040959 t plus 80 is our function. So what is x of 10? Well, plug that in, 270 e to the k, which I have stored. So I'm going to go alpha k times 10, close parenthesis, plus 80. I got 259.259. So approximately 259 degrees Fahrenheit. Sound reasonable? I should check my. Yep, that's reasonable. All right, and then the next question is when, so this one's asking about time, will it be 100 degrees Fahrenheit? So now we take our x and we plug in 100 for x. And we solve this. I'm just going to put k for t. So subtract 80 from both sides. Divide both sides by 270. And take ln of both sides. Ln of 2 over 27, just reducing that fraction, is equal to the power. And so time is ln of 2 over 27 divided by k, which I have on my calculator again. So I can type in ln of 2 divided by 27, close the parentheses, and divide by alpha k. And I got 63.544. Or, you know, about 63.5 minutes. Or 1 hour and 3.5 minutes. That's when it's safe to eat. Any questions on that one? All right. How are we doing on time? Good, good, good. Mixture. Actually, should we do the dead guy problem?
Yes, do the dead guy problem.
Is it's a cooling problem. All right, let me go back to my other screen because I have it over here. These are just the questions that I found. Let's see, where is it? Here. A dead body was found within a closed room. Can you see it? Question 5 here. Maybe I can blow it up
Yes.
a little bit. Yeah, so this is it. Dead body was found within a closed room of a house where the temperature was a constant 65 degrees Fahrenheit. At the time of discovery, the core temperature of the body was determined to be 80 degrees Fahrenheit. 1 hour later, a second measurement showed that the core temperature of the body was 75 degrees Fahrenheit. Assume that the time of death corresponds to T equals 0 and that the core temperature at that time was 98.6 degrees Fahrenheit. Determine how many hours elapsed before the body was found. They said hint, let T1 greater than 0 denote the time that the body was discovered. Yeah, I just use T, but that's a good idea because it is a specific T. All right, and tell you the truth, just for the sake of time, I'm going to show you where I have it worked out, but I'll go slowly through the steps. It is, I believe it's here. No? Ah, here. There we go. So we've got room temperature equal, oh, you can't see it, can you? I need to stop sharing here. Go back to here. Okay. So here's where I have also the review. I'll post this as well. Review of Newton's law of cooling with the ambient temperature being T or T sub M in the textbook. I've got a page reference for the textbook. And then the temperature of the object is X or X of T. In the textbook, they call it capital T of T, but that's kind of a lot of T's. So I like X better, definitely. All right, so number 5, we've got this problem where the room temperature is 65 degrees Fahrenheit. The core temperature of the dead body when found was 80 degrees Fahrenheit. 1 hour later, it was 75 degrees Fahrenheit. So time of death is T equals 0, and then it was 98.6. How many hours until it was found? Okay, so one way to kind of write down the information is in a table, as opposed to, you know, when I did it for the last problem, I just said X of 0 is this and X of 5 is this. And you can also do it in a table, you know, what is T and what is X to keep it straight. So when T is 0, X is 98.6. And then this is what they said, call this T1, which is better because it's a specific time, right? And this is T1 plus 1. 1 hour later, the temperature is 75 degrees. All right, so that's a good way to organize that. So we, again, have this differential equation, plugging in 65 for the ambient temperature. We can then use the fact that it's separable to get the function for X right here. All right, same steps that we just went through, right? Divide by the quantity involving X, integrate both sides, exponentiate both sides to undo the logarithm. The e to the ln, of course, kind of cancels that out. And then e to this quantity, you know, that's where you've got e to the kt times e to the c. And then this e to the c becomes this other c. All right, so then we take the fact that when T is, what did I do here? Sorry. What the heck did I do here? I don't know what did I close there. Have this, I used the initial value. Okay, here, I found C. This is using the initial value, because when you plug in T equals 0, e to the 0 is 1, and 98.6 is the temperature at time 0, right? So plug in T equals 0 and X equal 98.6. And then that allows you to solve for C. Okay, so this is the function. So if they asked, you know, what is X of T or A of T, that's what they're asking for, this expression right here. All right, so then we have these two pieces of information that you can basically set up two equations for. It's 80 degrees at time T1, this is a T1 now, and it's 75 degrees at time T1 plus 1, 1 hour later. So those two actually, you can solve for the exponential. And so e to the kt1 is this fraction. Subtract 65 from 80, you get 15. Whereas e to the k times t1 plus k, just distributing the k here, gives you this fraction. 10 is 75 minus 65, and then divided by 33.6. So then there's probably other ways to do this, but I'd use the fact that that e to the k times e to the kt here. I need some space. Where can I write this? All right, so first of all, hopefully you see where I got this equation and this equation, right? From putting in that x of t1 is 80 and x of t1 plus 1 is 75. So plugging in 80 and 75 for x, and then t1 and t1 plus 1. So we don't know what k is, but that's okay, because we can say we can solve these for the exponentials and then use the fact that this exponential right here is e to the kt1 times e to the k. So then what I did was I substituted this fraction in for e to the kt1 here, and that's where this equation came from. This right here is e to the kt1. So then if you multiply both sides by 33.6 and divide both sides by 15, you get e to the k is 2/3. So then plugging that in to the original function, we've got x equals 33.6 e to the kt plus 65. And that's 33.6 e to the k to the t. So that plus 65. So this is 2/3. And actually, I believe I went back to this up here, the e to the kt1 being that, because I wanted to solve for t1. I want to know what is t1. So this is actually t1 right here. So this went better the first time around. So I've got x e to the kt1 equals 15 over 33.6. And so that's e to the k to the t1. Yeah, I don't have to even have to go back to the original equation at all. Sorry. I just used the fact that I had e to the kt1. Let me move this over here. E to the kt1 equals 15 over 33.6. And I found what e to the k is. So I can plug in that 2/3 is e to the k. And then e to the kt1 is the same thing as e to the k to the t1. Power to a power, you multiply.
Can I ask a quick question?
Mm-hmm.
A little confused, the line above that,
Mm-hmm.
where you get to the other side where you have the ln over the ln. How does that work? I think I might have missed something.
Okay, yeah, that was a jump. Let me show you. So I've got you've got the 2/3 to the T1 equal this fraction, right? So far? That's
Okay, yes, I've got that.
Okay, so if you take ln both sides, then you can use the property of exponents that says you can bring that out in front.
Okay, that's what I was forgetting.
Yeah, and then divide both sides by the ln of 2/3. So ln of this fraction divided by ln of 2/3 actually gives you your answer, that 1.989 or 2.0.
Okay, perfect. Thank you.
Sure thing. Anybody else have a question on any step along there? That was that. Yeah, so there again, there might be a better or different way to get that time, but this worked. And I will post that later. How about a short break?
Sounds good.
All right, it is 6:36. Let's pick up again at 6:43. Hang on, let me turn this off. I'll put it in the chat. Back at 6. Let's go 6:45. All right, start the recording back up. Okay, so mixture problems next. Right, we didn't do any mixtures yet. We did, yeah, that was next. We did the dead guy, which wasn't as much fun as I thought it was going to be. All right, so number 3 from the apps handout says a tank initially contains 50 gallons of pure water. Let's see if I can get this to pull up. At t equals 0, there it is. At t equals 0, a solution containing 2 pounds of dissolved salt per gallon flows into the tank at a rate of 3 gallons per minute. The mixture flows out of the tank at the same rate. How much salt is in the tank at any time t greater than 0? And how much is present at t equal 25 minutes? And how much salt is present after a long time, which is basically looking for kind of, you know, the limit as t goes to infinity. Does it level off? All right, so for mixture problems, the basic idea is up here somewhere. Here. Looking at how much flows in, or what's the rate of the substance flowing in and the rate at which the substance flows out. And that difference should be the rate of change of the substance. So pretty simple model. The tough part is just, you know, kind of putting it together for a given problem. All right, so let's see what we got. Maybe I'll just write dx dt equals, oops, come on. There it comes. A little bit slow today. Dx dt equals in minus out. Okay, and we've got initially 50 gallons of pure water. So notice what that says is that the initial amount at time 0 is 0, right? Because it's pure water, the initial amount of salt. And that's what dx dt is, of course, is the rate of change of the amount of salt in the tank, right? Rate of change of the amount of salt. Okay, so then it says at t equals 0, a solution, okay, at time equals 0, a solution containing 2 pounds of dissolved salt per gallon flows in at the rate of 3 gallons per minute. And then the mixture flows out. Just saying it flows out at the same rate. Okay. How much salt is in the tank at any time? Is in the tank at time t. At time t greater than 0. In other words, what is x of t? What's that function? Okay, so we have dx dt equal, all right, let's look at, in fact, you know, of course it's in minus out. I wrote that up above. Let's look at what's the in and what's the out. So the in is going to be the 2 pounds per gallon that's flowing at 3 gallons per minute. Notice we can cancel the gallons and get that that is flowing in at a rate of 2 pounds per minute. Okay. And then what flows out?
Wouldn't a 3 be involved though?
Oh, excuse me. Yes, 6. Just checking to see if you're paying attention. Good job. All right, so out. What do we have going out? So here we have the same rate, the 3 gallons per minute. But how much is there? Well, that's where x comes into play, the variable, right? X is how much is in it at a certain time. And how many gallons? I want to say 50. Hang on. Thinking this is just 50. Yeah, that's all it is. We have X and then we have 50 gallons. So X pounds per 50 gallon tank is, you know, how much salt is in the tank. And it's flowing out at a rate of 3 gallons per minute. So that's going to be 3/50th X. Okay, so our equation is dx dt equals 6 minus 3/50th X. And this could be made into a separable, but I'm going to show you solving this as linear. So if we bring the x term over, it's a very simple linear equation. And this is in standard form because the initial coefficient is 1. Here's that, remember that p of x that we used for the integrating factor. And this is q of x. Really, really simple. So our integrating factor is e to the integral of 3/50 dt, and this is mu of t, excuse me. Our variable, that's the bad thing about using x now for our dependent variable, is it kind of can get confusing right there. T is our independent variable. T is like x and x is like y. All right, so this is e to the 3/50 t. Okay, multiply the equation through by e to the 3/50 t. All right, then what?
That entire left side is the derivative of
Good,
the integrating factor times x.
you got it. The integrating factor times, it used to be y, now it's x. Because sure enough, there's that function times the derivative of x. There's the derivative of that function, because that 3/50 would pull out by the chain rule, times x. All right, so now what we need to do is integrate both sides. And we get that and that. This is going to be e to the 3/50 t times x. And this is what? We've got that 6, which we want to divide by 3/50, don't we? Because the antiderivative would be that divided by 3/50, so times 50/3. So that'll reduce plus some constant. And if we divide everything by e to the 3/50 t, we're going to get 100 here, the 50 times 2, plus our constant. And I was going to put it over that, but instead of over that, let's write it as times e to the negative 3/50 t. Because dividing through by e to the 3/50 t is the same thing as multiplying by e to the negative 3/50 t. So there's our equation, and then we want to use the initial value to see what c is. Initial value again is that x is 0 when t is 0. And if t is 0, you just get 1. E to the 0 is 1. So c is negative 100. So 100 minus 100 e to the negative 3/50 t is our function, and now we can answer the questions. So this is how much is in the tank at any time t. How much is present after 25 minutes? Well, plug that in for t. 100 minus 100 e to the negative 3/50th times 25. So e to the negative 3/2 times 100 subtracted from 100. Let's see if I can get that. And of course, here we just want to approximate, and your homework always tells you how many decimal places to give. Let's see what this one gives me. 100 e to the negative 3/2. All right, I got 77.687. Let me just round to 7. 77.7. Anybody else get that? Yeah, 77.687.
Yeah, that's the same thing I got.
Yay. Looks like the same thing I got last time I did it too, so that's good news. And this is, of course, pounds of salt. And then they want to know how much salt is present after a long time. In other words, and this is actually what your homework is going to ask you, what is the limit as t goes to infinity of x of t after a long time? So you want to notice that, that function actually does level off, because this exponential with the negative coefficient is decay, and this goes to 0. Remember? Decay. So 100 times something that's going to 0 is also going to go to 0. So this guy is your limit. 100 pounds. So it is going to level off, so that's pretty much what you end up with. All right, we got to do a circuit, don't we? So let's go back to a homework problem. I think I actually did one and got it right. Where'd it go? Where'd it go? All right, I'm gonna actually just write it down here instead of switching screens and switching back. This is my number 7 from WebAssign. So yours will be the same except for possibly numbers. It says a 10-volt electromotive force. Electromotive. Is applied to an LR series circuit. In which the inductance is 0.1 Henry. And the resistance is 30 ohms. Henries and ohms. All right. Find the current I of t. If I of 0 is 0. At time 0, the initial current is 0. All right, so here's where we go to the current stuff. Circuit stuff. Hang on, let me close my chat here. So we've got this circuit and these various laws, and we want something involving I. So what we're going to use is this right here. Oops, I can't read on this. Well, it's this one. It's where it says the sum of the voltage drops is equal to this, but we don't have a 1 over CQ. We just have Li prime plus Ri equals E. So it's really simple. Let me make sure. Where's my notes on this? 7, 9. Yeah, here. Okay, so let me go back and kind of summarize that. What we've got is, we've got L is the inductance, which is 0.1 Henry. We've got R, the resistance, is 30 ohms. And C, we don't have C. So we have E, the voltage is 10. And it's constant, which is nice. It could be a function. But basically the equation you're going to use is Li prime plus R I equals E or possibly E of T. Okay, so that's really the simplest version of this formula that is all you really need here. Or you could view it as L di dt plus R times I equals E or E of T. Okay, so what's our equation? Well, we just have 0.1 di dt plus 30 times I equals 10. Yeah, there's a 1 over CQ that is the capacitor. Well, we don't have in this. Yeah, chapter 5, we'll be looking at circuits where we have we read it in terms of charge, and we have a Q double prime, and it's a second order linear equation. So we have to wait till then when we study how to solve second order. So this one is linear first order. We only need to put it in standard form, which remember is to get that initial coefficient to be 1. So we're dividing by a tenth. Dividing by 1/10 is the same thing as multiplying by 10. So the integrating factor, mu of t, once again, is e to the integral of a constant. So that's going to give us e to the 300t. When you multiply through, similarly to the last one we did, we get its derivative here, right? 300 e to the 300t is its derivative times I equals 100 e to the 300t. Don't forget to multiply it by the other side. And then this is the derivative of, oops, sorry. Derivative of e to the 300t times I. So we can take the integral of both sides with respect to t. And I need a new page. One more page. e to the 300t times I is 1/3, 100 divided by 300, e to the 300t, plus some constant. So divide through by e to the 300t, which just gives us the 1/3. And so that's going to be c e to the negative 300t. So that's our equation with the arbitrary constant. And then we want to use the initial condition that the initial current is 0. So plugging in 0 for I and 0 for t gives you c equals negative 1/3. Okay, so again, you might see some similarities to the last problem where our function I, or I of t, is 1/3 minus 1/3 e to the negative 300t. So then, similarly to the last one, it said determine the current as time goes to infinity. So what is the limit as t goes to infinity of I of t? Now that exponential goes to 0, so that whole thing goes to 0. Looks like it's going to be 1/3. And what are the units here for current? What is the units for current? Do you guys know? I should know.
Amps.
Amps, of course. Thank you. Good, good. All right, how's that? Enough for tonight? So I will come up with 2, 3 problems. It would be like, take home problems. That you will do. So I will, in fact, I'll post them. So posted on the folder where you're supposed to turn them in. If you can't find it, I'll show you next class period. Where you turn yours in. So there's Dropbox formulas for folders. I think it's under assignments, something like that. Assignments / Dropbox. So what you're gonna do is go to that folder to see the document that has the questions on them, and you're gonna work out the questions, and you can get help from your friends. Don't go to a teacher or a tutor, please. But you can work with each other. And then scan your write-up using a phone app or whatever you can find. Don't just take pictures. Use some sort of scanning app. It's just as easy and gives much better quality. And that way you can put several pages into a single file. And then you'll post that file into that folder before class in a week when it's due.
So when will you be posting these?
So I'll post them before next class, as soon as I get them ready. I will, in fact, I'll send out an email when I get them posted so you can know. But it'll be at least by before or by next class period. See if I go here to my other screen. I can show you. Oh, here's the question we just did, by the way. I can show you where that is. Weird. There we go. Tutors. Oh, did y'all see this announcement I posted? The Cengage rep said that if you are having trouble and still using a free access to the WebAssign, you can contact them. They're having like Zoom office hours to help you get logged in or whatever if you're having trouble and you're still using the free version, because that'll probably expire if it hasn't already. Okay, under assignments, right there, I have to make some extra folders. So like there'll be a folder there that says take home problems for test 1. Right, and then I'm going to actually add the attachment here that has that file so that when you go in, you'll see that file. See, now it's there, but I can like move it. Yeah, I'll rearrange it so it's at the top. So that's where I'll be posted, and that's then where you will submit your solutions. And then when we have the test, we'll take the test in class, and then as soon as you finish with the test in class, you'll scan and upload your work for the in-class part, and you have 15 minutes after you log out of Zoom to upload your work. And also you'll want to upload the page that your cheat sheet for that test. All right, well, y'all have a good night.
Okay.
Thanks.
Wait, I got a question.
Thanks. Have a good night.
Thanks. What's your question?
When did take-home problems due?
They will be due in a week on test day. So you'll have the weekend to do them.
Okay. Okay, thank you.
You're welcome.
Bye.
Bye.